everybody ready? Got some thumbs ups?
Let me just bring this window down here so I can at least switch easily. So everybody seems to be ready. Okay, so let's go. So the first thing we need to think is, okay, what is a circular linked list? Let's just draw. So I'll draw it like this, like a donut, right? And we have buckets. So the one thing that I want you to think about is that the circular linked list I'm not going to add linked in there because a circular list is a data structure we come up with, right? This is something that we're making up, as with any data structure, you can come up with any data structure you can think about. And now the word linked in there implies that we're going to be using a list of linked nodes. Now, you could also implement this using an array, but you know the constraints that we have when we're using arrays. So we're going to use a linked list. So this will be a circular linked list. What that implies is that each one of these buckets is a node, and it has a pointer to the next node. Pointer to the next node, pointer to the next node. Is everybody here familiar with what these nodes are? Let me show this up. Yeah, okay, so great. So we can go straight into the concept. So everybody knows what a node is. And a node, it's basically, a node is nothing else but something that holds a piece of data, this is what is of interest to us, and a pointer to another node, either next, or we can also have a pointer to a previous node. We are gonna, since we're gonna work with a singular linked list, just one pointer to the next node. That is so, we're gonna make things a little more difficult on ourselves. The one thing we need when we have a linked list is that we have a point of entrance. We need to get to the linked list somehow. So usually you will have a head. This is how you get an entrance. This is how you get a hold of the whole list. The nodes are pointing to other nodes, but if there is no way to get a hold of the first node, you cannot. In fact, the garbage collector will take away your whole list, and there's nothing you can do. Now, often it's useful to also have a tail. This is, and I don't know what the constraints that you have right now with the one that you have to implement are, but often it's useful to have a tail. This is, so let's say if you want to remove from the head, you can just do it because you have a pointer to the head. Or if you want to add at the head, you can also do it. And if you want to add at the tail, you can also do it because you have a pointer to the tail. But this, you you can also omit this, in which case you have to go around the circular list if you want to add a new node. Now, I am working under the assumption that you all know what a node looks like. But let's say, and a node is just a box that holds some value. Let's say it holds an integer 1 as a pointer to another box. Let's say it holds the integer 2, and it has a pointer to another box. Oh, it could be a pointer to null, which is nothing. And then we have the head here. And in this case, since it's a circular linked list, this will be pointing to the one before to make it circular. Now, we have to think about a few base cases, right? When the circular linked list is empty. So what are we going to do with the circular linked list is empty? And I am also working under the assumption that we are not going to have a dummy node, but we could make this a dummy. I don't know. It's do you want to do that, or do you want to work without a dummy node? I'm gonna ask here.
I personally think that there are pros and cons. I mean, I like working with a dummy because it makes things easier. But
Yeah.
you know, there's constraints if you're not allowed to have a dummy. So that's also good to know how to do.
Yeah. So no dummy then. Okay. So if the linked list is empty, assuming we don't have a dummy node, that means head is gonna be null, and then tail will be also pointing to head right here, right? Which will be null. So this is one base case. Now there's another one. What happens if there's only one element in the list? That means head is pointing to a box, and then this box has a next pointer, right? So what will next be pointing to? What will next be pointing to?
Anyone have any guesses next might be pointing to? If there's no dummy node and there's only one node in the list.
It's just one node. This is the first node that gets into the circular linked list. Well, in this case, this will be pointing to itself, right? And tail, this is the last node, so tail will be pointing to the same node, right? So we need to make sure that if it's the first value that comes in, it's going next. The next pointer will be pointing to itself. Make sense? We have two: empty, just one element. Now, when we are designing a data structure, I'm gonna right here. So let's say I am designing my circular linked list right here. I have to think, okay, what am I going to have in my list? I'm going to have some data members, right, that are going to be holding data. One of them is going to be head, as we said. I'm going to make mine have a tail as well, since that is useful. And it's often useful to have a size pointer, a size holder. Then we're going to have methods. What methods do we want to have in a circular linked list? And now this is, if you want to make it generic, so it can be used for any purposes, then you have to think about that. If you are making it for a single purpose, then you probably already know what methods you need. But let's say this is generic. Let's say we want to be able to obviously push, and I'm gonna say push to the front of the list, or push to the at the head. But push front is usually a good name for it. And then we're gonna push an element E. Let's say if you're making it generic, we want to be able to also pop. And usually when you pop, and this is true for Java, it's not true for other languages. Like in C++, they made it so these container classes don't return anything when you pop. They return a Boolean value indicating if it was possible to pop the value or not. But in Java, it is common that you return an element and you will return null if there was no element, right? So we're going to pop from the front. Oops. How did I get out of there? Then we could also do pushback if we want. And also, it's equivalent. And then I made a typo here. Element and then pop back, right? Then what else do we want to have in there? There's usually a pick, right? Pick. I'll just pick front end. And this will return me an element. You also usually want to know the size, and you usually want to know if it's empty. And this size will return an int, and this is empty, will return a Boolean. So anything that is missing from there, push from, push front, push back. And this is working under the assumption that this will behave just like a queue, like a single link queue that is circular. Now, it's are we all good on the design?
Does anyone have any questions as to why we have some of these methods or some of these variables to hold data about the circular linked list? Or no questions? Everyone's good.
No question. Okay. Okay, great. So now what I did here, I stubbed my class. I have a class that it's a circle link class, and it has a private node down here. I made it generic just because, and we don't really need to have constructors, but I just included them in there. Usually because the node is private to the class, we can safely expose the data and the next pointer. And then what I did in main, I just made this is my sanity test, is what I call it. It just to make sure it runs, I put some dummy returns in there, and as you see, it runs, but it prints some empty arrays, and I just put some dummy return objects in this methods that will return for now before we start implementing it. So the first one, in is empty. We just know that if the size is 0, we'll return true, otherwise false. And in the size getter, we just return the size, right? Now, let's start implementing it. As I said, there are a few cases. One of them is when it's empty. And so when we create the circular linked list for the first time, it will be empty. So what we're gonna do is we're just gonna say head is null, and then tail is gonna be pointing to head, and then we're gonna say size is 0, and that takes care of the constructor. And we can always run it and to make sure it runs, because we have stopped the rest of the classes, and I have my sanity test here that creates a constructor. I don't know if it works correctly right now, but that it runs. Now, we start implementing the push front. We are going to, where is my board? Oh, here it is. So if we're going to insert, let's say we have this circle linked list here. Oh gosh. And I'm going to change color. We have this circle linked list here. And I want to insert a node right at this point, before whatever was the first node in there. So what do we do? First, we have to create a new box, a new node, with whatever value is holding, right? And then the first thing that I tend to do is, and I see this as, oh gosh, I see this as anchoring my node to the chain. The first thing I need to do, I need to anchor my node to the chain. Right here, because if I am going to delete this link, I am going to rewire this one here, and I'm going to rewire it to the node that just came in. Now, the order matters, because if I don't hook my new node to the chain and rewire this first, what will happen? The garbage collector will take the whole list. It will just take what was there before and leave me with nothing but this new node. So the first thing that you want to do is you come and you grab onto the first node that is in there, and then you rewire head to this, to my new node, right?
And a great visual I think about is, like, you know, any of those space movies where you have an astronaut who's holding on to something, and they have to hold on to the spaceship, but they also have to hang on to this other part. And if they let go of the spaceship before they've attached the other part, then, you know, they'll just float off.
You'll just like fly away.
Just fly away.
So I create my new node, right? Now I hook myself to the first node that is there, which head is pointing to. Now, again, remember that there is a special case. When this is the first node that is coming in, and before this node, the list was empty. So that is another one that we have to take care of. So in this case, we have here like head is null. Let's say that says null. And tail is also null. So since there is nothing you have to get a hold of, you just put yourself right here in this position. Just force yourself in. So that's what we're gonna, so we have here if head equals tail, and I could say if head equals null, but this will take care of two special cases. The other special case in this case is this other one that I generate when I only have one element, and both of them, both tail and head are pointing to that element, and the element is pointing to itself. So in that case, what I want to do is I want to insert the new value in here. This is becoming messy. I'm going to erase this. This is becoming messy. So again, there's only one element. Let's say it has the value 1, and this is head, and this is tail, and this is pointing to itself. Now I want to insert a new one in here, and I'm going to change color. So now this new element right here will come in, get a hold of this one here, and then head is gonna point to itself. So this special case is because both tail and head are pointing to the same one, but it happens to be the same if tail is pointing to head as well, right? So I can just rewire to wherever tail was pointing to, and then let's see. Yeah, I'm getting a little confused. No, this will not take care of that. This will take care of that if I have a dummy node, but I don't have a dummy node, so I have to account for head equals null. Sorry about that. So going back, if head equals null, I put my new node in there. So I just say head equals my new node. And then this is also the last node, right? So both head and tail are that new node that came in because it was empty. Else, if head wasn't null, then I am going to say, my new node, its next pointer is going to, again, back to here, it's going to point to wherever head was pointing to, and then head is going to point to my new node. So this is wherever head was pointing to is what my next is going to point to, and then head is going to be pointing to my new node. And tail won't change because it was already, it's at the end, doesn't matter. And then the last thing we do, of course, we increase the size. Right. Now I can run it again, but this won't change anything because what I am printing out, oh no, it exits with process 1. Teacher. Process finish with exactly 1. And this is why it's good to have some sanity test. And the coolest container in cost class. Java line 14. Where I am trying to get, I'm trying to pop back, but there is nothing to pop back. That's line 14 because I haven't implemented it yet. So I guess I have to implement pop back. No, by sanity test, I mean just in general. So I write in main what I believe my class should be doing, and then I come and then I start implementing it. But every time I implement something, then I run it to make sure I didn't break anything. That's what I tend to do. So new node. Head, I'm just double checking myself. Next is pointing to head, and head is going to point to the new node. And then we increase the size. If head was null, then we just put it in there. And then tail also has to be pointing to that new node because, well, it was pointing to null as well. That makes sense. Let's say I am going to comment out. I'm going to comment this out. And I have a test for pick here. And since pick tend to be fairly easy, I'm just going to implement pick, which pick will return whatever is at the front. I should call it pick front, but yeah, I should probably name it pick front. And then yeah, and then it's gonna tell me that I need to return something. So pick is going to return head the data, but there is a problem, right? Because head could be null, and this is why dummy nodes are usually good, because I'm going to say, and then if head, I have to make sure I test for null, otherwise this is going to give me a segmentation fault. Or if it's null, then I'm just going to say null, else. I could put a return in there. I'm just going to do that. I'm not going to do the else because I can just return here. I'm just going to return null. Yeah. Otherwise, I'll return whatever data is in head. More related problem. Oh, yeah, because I changed the name. So yeah, it works. I put 34, I push 34 to the front, and then I pick, and then it gives me 34, right? So I know that that method worked. Let's see if it works when it is empty. And this is just something I put in here so I don't have to be writing this live. That is because I didn't comment this out. Sorry, I forgot to comment that one out. It is so, and I know that the push front is working now because I see the 6 in there. Yeah, but yeah, if it's empty, then it just returns null, right? Which is what we want. Is what we want. There's nothing in there, so we return null. So that seems to be working. And I'm gonna just remove this, and I'm gonna put it at the very top because this is my sanity check. And then I'm gonna uncomment this, and some part of it should work, but then again, part of it will not work because I haven't implemented everything. Now, push front. We implemented push front, and let's implement pop front now. So what do we want to do in pop front? What does pop means? Let's forget for a moment that this is a circular linked list. And since we don't have a dummy, let's unfold the list. Let's unfold it and head, and then we have one element. It's pointing to the next. This is pointing to the next. If I can draw boxes, that would be great. Pointing to the next. So what we want to do is we want to grab this box right here. We want to grab this box. We want to get whatever is in the box. This is like me opening a Christmas gift, right? I will grab the box. I will get wherever my gift was, and then I will throw it away. And of course, I have to rewire head. Otherwise, this whole chain will be thrown away. So that's what I want to do. Now, there's always special cases, right? We always have to remember there's a special case when the head is empty. There is a special case when there's only one element in the list. Pop front. So I'm just going to substitute this. Okay, so what is the first thing we do? We need to make sure we are not dealing with the case where head is null. What do we do if head is null? What do we do if head is if there's nothing there? What do we do in this case?
Do we return an empty list?
Well, there's nothing to do, right? And there's nothing there, so we just return null, and there's nothing to pop. All right, now we have the other case where there's only one element in the list. In that case, both tail and head are pointing to the same element, right? So I don't even need to take care of that. Well, yes, I do. Because if it's pointing to itself, I can rewire that to itself. I will have to rewire that to null. So, and I can check if head is pointing to the same thing as tail is pointing to. In that case, I could also check if size is 1. That will effectively do the same thing. Or I can just check when head and tail are pointing to the same box. Does that make sense? Everybody?
Everybody,
make sense?
Okay. Sense? Thumbs up? Thumbs down?
Okay. So if both head and tail are pointing to the same box, then I will. And what I tend to do is, I tend to do this, right? I tend to just say, okay, I have an E element. This E element is the variable that's going to hold what I am going to return. I usually call this one result, but in this case, I will call it element. So if head is pointing to tail, they're the same thing. Head is not null because otherwise it would have returned. So I'm sure I have something in there, but I only have 1. So now element is going to be whatever head data is. I'm sure I have some data, right? And then I'm going to say head, it's going to be null now because there was only 1 element. Now it's empty, right? I took the element. Although, let's do this instead. I am sure I have something. I am sure I have something. So I just need to do this. If head, so I'm sure I have something, so I just take it. If head is pointing to tail, then I have to set head to null because I can't set head to anything else. Or in this case, head is pointing to null. Else head dot next, it's going to, I'm going to skip to the next element. So I'm going to say head, and remember this is head and this is head next, right? So I am going to skip to the next element. So head equals head dot next. That should take care of rewiring. So the rewiring is either head ends up being null or head is pointing to wherever head next was pointing to now, effectively skipping this element that I just popped out. This is the equivalent of throwing away the box. Make sense? Now, so I have my element. I have rewired head. So I can just return. Let's see, what is element? That's what I named it. And now, here, since both head and tail are pointing to the same box, I also have to set tail to head to make sure tail is not pointing to the same box again. And I could say null as well, because head is null. It doesn't matter in this case. And then what else? We're forgetting something, right? It's very important to reduce the size. Make sense? And then, so I'm going to run it again. Now, what is this? The pop back. Exception cannot be cast to class. Object. Okay, yeah, this is type erasure. Where is it? And this is this one that is a pop back. It's giving me that issue. So I'm going to just pick front. That works. Push front. Oh, I did pop front. Okay, so then I can just comment this out, and then the pop front should work. So you see, pop front works. I commented this out because since I haven't implemented pop back, this is giving me an issue, but that should be resolved when we implement pop back. Now, there are two more that are important, which is push back and pop back. Now, let's do pop back in case, because this is really important, and in case we run out of time, we do it. The issue with pop back is that, so even though I have a pointer to tail, and then I don't know why I erased this here. Even though I have a pointer to tail, in order for me to pop, in order for me to extract this box from here and remove it from the list, I have to rewire, I have to grab this arrow, and I have to rewire this arrow to here. Now, what is the problem with that? Can somebody tell me what the problem with that is? Okay, they're shy. So the problem with this is that in order for me to do this, I need to have a pointer to this. I need to have a pointer to the tail -1 or whatever you want to call this, right? I need to know what this box is so I can grab the arrow and skip to the next one. Now,
There was, if this was if our nodes didn't have just a next pointer, but if it also had a before, could we have done a tail dot before to point to the head?
Yes, that tends to be the solution to work around that issue, right? If you have a double linked list, then you have another arrow pointing back. So now you can follow this arrow, and you can get a hold of these nodes right here, and then grab the arrow next and rewire. And then you can rewire this one's arrow to here as well, right? But this is a singly linked list, so we have to go around the list.
We're gonna have to go all the way around the list because we don't have those double pointers.
Yeah, because we don't have the back, so we have to go all around the list. So how do we do that? How do we go around the list? I usually create a node and I name it current. And this current node is going to start somewhere, right? It's going to start at the head. Now, again, because we don't have a dummy node, we have to take care of the case where head is null. So again, and this is, if you have a dummy node, you can avoid all this checking for when head is null. But since we decided not to do that, so we have to. In this case, we just return null, right? And then we start at the head, and then we're going to go around, and we're going to say, okay, if I am going to stop one before the tail, right? So if my arrow, if my arrow is pointing to tail, then I will stop. Make sense? Now there's that case. Let's check. There's this case where there's only one. Does this work? And then I don't know because I haven't done it. I didn't prepare. So if there's only one box, I'm gonna say I start ahead, and if my next is pointing to tail, I'll stop. And that is not true. But it is true, but I am tail. I am not the previous one, tail. Because otherwise I will be inserting a node in front of tail. And what I want is to insert it here. So yeah, we have to take care of that. That will be a special case. Oh, that is for inserting. For popping. I will be popping. Yeah, pop back. Yeah, I'll just take care of that one up there, so we don't have to worry. So if there's only one element, so if head equals tail again, what we do is we just pop that one, set it to 0, and return. Or yeah, that's so I'm just gonna say I'm gonna get a hold of my element. This is because I am dealing with the tail, so I'm popping back, which is the same. They are the same, but I want to be proper. And then since there is only one element in this case, it will be null. It will be null, and I will return my value. And then that ends there. That takes care of the two cases. I could do it differently, but this is easier. This is easier, more straightforward. So now I'm sure I have at least 2 elements in the list. And I can safely say, while my current node, arrow, is not pointing to tail, then I keep going. I keep moving along. I update current to wherever next is going to. This is the equivalent of going around. This is the equivalent of going around. I start here, and I'm going to change color. I start here, and I ask, is my arrow pointing to tail? No. Then, okay, then I go to the next one. Is my arrow pointing to tail? No. Then I move to the next one, and I go around until I hit this one. And I ask, is my arrow pointing to tail? Oh, yes, it is. So then I get out of the loop. And what I have is this box here. This is my box at the end of the loop. right? So now I know current is the box that is before the tail. So I can get my element from, I can get the element from that next, which is tail, in case I could get it from either one. I'll do current next because just because the data. So that is the last element, the one that is ahead of me. And now I rewire. I say current. Current next. Let's see it in the, so current next. So my current arrow is going to point to wherever this arrow is pointing to. So current next is going to be current next. Make sense? This is like you're a tender, right? And then you ask next, and you see the guy lifts his head, and then you point to the door, and then you say no, next. Okay, never mind, that was a bad one. But anyway, so we rewire the next, and then we reduce the size, and then we return our element that we have now. Right? Make sense? I should now be able to run this, but there is no pushback. So that one, I haven't implemented that one, but I have implemented this. But this is now popping from the, no, this is popping from the front. This is popping from the back. So I'm commenting out some code because otherwise it would interfere with my test. Yeah, that's why you do unit tests instead. Null pointer exception. Look at this. I am missing a case. Which one is it? Is there any confusion? I see the question in the chat. So if it's null, just return null. And tail null. Oh, this is the thing. So I'm forgetting here to return the size, to reduce the size to 1. Yeah, I have to do this. Element to size. This is not going to take care of this error. I know. So there's something wrong here. I'm going to put the stop right here. I'm going to debug. So, and this is nice, right? You see that I pushed 1, 2, 3, 4, 5, 6, and I pushed them at the front. So the last one that I pushed was 6. So that is the one that is at the head of the list with a value of 6. And then the next one has a value of 5. Then the next is 4. Then the next is 3. You see how I'm drilling in. Now, that's not what I wanted to show. So we're going to debug. For some reason, it's giving me a null pointer exception. So I'm just going to step over these just to see what my current is. current right here. My current is 6, and next is 5. So step over. Now my current after this should be pointing to 5. Yep. I'm going all around. Step over. 2, 4, 3, 2. Now 1. Here's gonna be the area. It's pointing to 2. Then, oh, that's interesting. Next is null. Should never be null. Next 1 is null. It should never be null. Where is that happening? It's sorry about the debugging.
Great. You know, it's always and which IDE are you using, Hardy?
This is IntelliJ, and I just started using it today, by the way.
I kind of like the look of this debugger.
Right. You can drill into the objects. So now what's going on here is that so you see I stopped 1 before the last one. The tail here is 1 because that was the first element that I inserted. But you see its next pointer is null, but it should never be null. So when I inserted 1 here, yes, that is the reason. You see it now? Do you see?
Why is it? No, I'm not quite seeing it. Why is it null?
Because when you see the special case here, when head is null, it should be pointing to itself. But I forgot that.
Oh, yeah.
I forgot that. And then the else, yeah, everything takes care of it. But here, new node, next, should be pointing to itself to make it truly circular.
That's it, yeah. Because if it's circular, it should never, you're right. If it's circular, it should never be null.
It should never be null. But you see how we found the source of the problem, right? Just because like we can drill. This is great about this IDE, and a lot of IDEs have this feature where you can look at the element, you can look at the variables, and if those variables have pointers or arrays, you can drill down. So anyways, so yeah, that is the issue. So now let's see. Oh, stop and rerun. Yes. So yeah. Now it's just pointing. It's always returning 1. That's another bug. But let me get the stopper. So if head equals tail, because yeah, that one is. So it's always going to do this because push front. Else, so also here, else increment size. So if it's null, I point to myself. Then again, we have other special case. And this is fun about this. Remember, when head equals tail. Yeah, and this is why I love dummy nodes, because
I know dummy nodes make it way easier.
yeah, dummy
honestly.
nodes take care of all these special cases.
My favorite are circular dummy nodes with doubly linked. So
Oh
pointing in
yeah,
both
yeah, right.
directions.
It makes things so much easier. But in this case, so if tail equal new nodes. So if tail is pointing to head, that means there's only one element. So then I have to rewire. I have to rewire tail. So if I push to the front, so this is the case, right? I push to the front, I rewire head to my new node. Now tail should be pointing to the new node. No, this should be fine. So there's something else going on. There's something else going on, and I'm going to put this. I'm going to put the stop right. Stop right. Let's see. Put stop there. And debug. So I know my new node. Let's see what head is. So it's 1, value of 1. And let's see where's tail. That is why. Where is tail? Oh, because it's not part of this, so it's gonna be just here. It's okay. Yeah, I see. So both are pointing to 1. I'm just gonna step over. You know that. So that is on the first insert, and then I'm going to back into main, step over, step in. Now I'm inserting data into the head, and tail is still pointing to. Okay. Yeah, now it's 3. Step into. Yeah, and tail is always pointing to 1, so that's good. That's code is good. So that's not what's giving me the issue. Oh, I had to stop here. I'm going to stop it. I'm going to run the debugger again. So tail is 1, head is 6. I'm going to step over. Then I have it's hard to see. I'm just gonna step over, and current is 6. Yeah, that's the first. Then current is 5. And current is 4. Current is 3. Current is 2. Okay. So now Okay, next should be 1. And when I step over, I should get up out of the loop. So I got out of the loop. That works. Now the data that I want to get is next, which is data. Which is 1 is in the tail, so that's good. So now current, the next. Oh, yeah, that is why. Since I removed that, that was my mistake. That was a brain fart. I need to, because I removed the tail, right? Mm-hmm. I removed the tail, so now I am the tail. I am the last element.
Oh, you have to put it back.
Yeah, so what happened is that, where is my tablet turned off.
You have to update the tail.
Yeah, you have to update the tail. Yeah, and I like, so now this arrow here, because it's still pointing to a node that it's supposed to, it has supposedly should have been taken away by the garbage collector, but it didn't, because tail still has a pointer to it. So now I need to rewire the tail to this, because this doesn't exist in the chain anymore, right? So yeah, that was the issue.
The garbage collector was coming by every so often and say, "Hey, you want to take this?" And the tail was hanging on to it. It's like, no.
The tail was like, no, this is mine.
It's my garbage bag.
So it works. It works now. But yeah, and this is good because we can see how we can debug. And honestly, this pop back tends to be the most complicated of all these methods, because you have to go around, find the node that is before the tail, grab the tail, remove it, and then rewire everything, right? And if you forget something, you get this odd behavior. But all you have to do is, like, you kind of get an idea of where is the problem coming from. And then you put the stop there, you run the debugger, and you step through, and you look at the elements, and you know what you're supposed to be seeing. And then you're like, okay, this is not what's happening. So what's going on? Like in this case, tail, I could tell tail is always 1, but why? And this is because, okay, yeah, I didn't update that here, right? Anyway.
And looking back on bugs, it's always like, oh, of course, it wasn't changing because it wasn't being updated. But
yeah,
at
that moment when you're debugging, it's like, what's going on here? So, yeah, the last one that we haven't implemented is pushback. So you see this pop front, we did pop back, and it's 12:10. It's a little past the hour. Do you want to implement pushback, or would you like me to share this file and you can implement it on your own?
Does anyone have any thoughts? Thumbs up if they want to, or you can type see more if you want to see more, or you can just have a thumbs up if you're good. I thought one thing I wanted to talk about briefly before the end of the session was about the time and space complexity of linked lists. Okay, David says he would like to see more.
Okay, time complexity.
Size says more. Okay, we got 2 mores.
Okay, so let's talk about time complexity just for a moment, because this is interesting. Okay, so we always think of time complexity in terms of how expensive it is in terms of n, right? We always use this n. So what is n? n is the number of elements in our data structure. In this case, like this wheel that I have here has 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so n in this case is 9. When we think about time complexity, we care about how it behaves, how the expense of doing computation on that data, how that expense increases as n increases. And we care about how the graph looks like, the asymptote of that. So if it looks like this, that is linear. That is linear, and it has some rate, some increasing rate, which is m. You've seen that, right? M equals y over x. How far goes up it goes per x, but it doesn't matter. So it's linear. If it goes like this, is exponential. And linear, usually we say linear is big O of n. If it's exponential, we usually say it's big O of n squared. Now, let's think about the circular list, and let's think about each one of these methods have a time complexity. Each one of them. Let's look at push front first, and let's look at the code. So you see in push front, what I am doing is, and let's say that each one of these computations, each one of these operations has a cost of 1. So, and usually this cost doesn't really matter. What matters is how it increases. But do you see any loops in here? That's the first question. Do you see any loops? There are no loops, right? All I am doing is I'm checking head, and I am inserting this value here at the head of this chain. Now, what do you think the time complexity of this is?
Would that be?
It doesn't matter.
Would that be so? Would it be the same no matter what, because you're always putting it in the front?
Yeah, it doesn't matter how big that is. You always putting it in the front. So this is big O of n. Pop front. Well, by the same analogy, we're just removing the element. There are no loops in there. It doesn't matter how big our data structure is, how many elements we have. We're just removing from the head. So again, this is big O of n. Now, let's take, because pushback, since we have a reference to the tail, and that's the reason I put that, is because that will make it this big O of n as well. Because again, we just have to look at the tail and put a new element in there. We haven't implemented it yet, but you will see.
Hardy, I have a question.
Mm-hmm.
So yes. I thought big O of n was linear time, right?
It's per big O. Oh, sorry, yeah. Yeah, thank you, Kristen. That was me. Yeah. No, you're right. This is big O of 1. And this is all right, because there are not very many data structures that can give you this. big O of 1. So sorry about that.
I was just reviewing it the other day, so I was like,
no, thank
that's
you,
good.
thank you.
That says that I'm learning though, because I'm trying to learn these things. And
Uh,
up until a few weeks ago, I was more confused about the differences between, big O of n,
yeah.
n squared, constant.
Yeah. No, thank you. That was like I know this, but yeah, we make mistakes, and that's normal, I guess. Let's try not to make those mistakes during an interview. So yeah, you're right. Big O of 1, and then the pop back. So this one is the interesting one, because in order to get the last element, we had to go through the whole chain, right? We check right here. We check each one of these elements, and until we got to 1 before the end. So as the chain grows bigger, when the chain is only 1, it's easy. When it's 2, we just check 2, right? 3, but as it grows larger, then you see the time complexity grows larger, grows like this, like this one. So this is big O of n. It grows in linear time as the size of our data increases. Now, this is why linked lists, are used for queues and stacks, because on a queue you just basically you push elements in, you push elements in, and then you pop them back. They come in and they come out at the other end. And if you want to insert here in the middle, then you have to walk through the list and insert it at some point. Now, one thing, and this is not something I did here, because indexes are kind of odd in when we talk about linked lists, right? But let's say this linked list have an index. Let's say this is index 1, this is index 2, this is index 3, this is index 4, right? And let's say this is not circular. So if you want to get element at position 3, I have to walk through. I have to check this. I have to go to the next one, and I have to go to the next one until I find it. And let's say we have 100 elements in there, and we want to look at element at position 99. We have to go through the whole chain until we find it. So if here in one of my methods, I had, let's say, I had return E element, and then I'm gonna say at index, and then I'm gonna pass an index. So if I have some, oh gosh, okay. So if I have a method like this, right? This is what I'm doing here. I want to look at the method element 99. So I will always have to go around the list until I find that element, and then this would also be big O of n, right? So if you have seen arrays, So arrays is just a block of memory, and each bucket has an index 0, 1, 2, 3, 4, 5, 6, 7, And you have seen that with arrays, if I want to get the element at index 5, I just jump right there. Because this is a block in memory that is contiguous, and I know the size of every bucket. I can calculate, like, have a pointer to the beginning of the array, and then if I know the size of each bucket, I can calculate the beginning of bucket number 5 in there, and that is the stone doing math, and it's very fast. So we say that this is big of 1, because it doesn't matter how big the array is. I can always move to the index that I want at constant time. That's not true with a linked list.
Could we also, on the little graph you have, that green graph, could we also see like where big O of 1 is in comparison to the other the other time complexities on the green graph with the arrows? So we can see how much faster it is than the other two.
Big O of 1. Yeah. Big O of 1 is, let's say, this is the cost of the, this is a cost y, and there's a number of elements n. As elements increase from 0 to n, this cost y never changes. That's what that will look like a flat line.
And the interesting thing about big O of 1 is that even though, and this graph kind of shows it too, it's like it doesn't, like the cost of setting up something might be higher than the time cost might be higher than, you know, a different big O, you know, it could be higher than big O n or big, you know, n squared. But because it's constant, it actually ends up taking less time overall, because the time doesn't grow with the number of elements.
The time doesn't grow, and the one thing with big O time complexity is that we care about how the expense of computing something increases as the size of the data grows large. For small size data, it usually doesn't matter. If we're dealing with just a few elements, it doesn't matter. But as we're dealing with the thousands, millions of data, that cost becomes really expensive. Now, usually, if you do math and you calculate the real cost, you will end up with something like this, like cost k plus n squared or something, and you know, there could be a constant a here and a constant b here, but all this is so small compared to n squared that we just say, oh, it's n squared. This really is insignificant. For big, for larger size of data, this is insignificant. We just say it's big O of n. So when we look at the code, and when we look at this, all this checking here and here, and all these other things that we are doing around, these are usually insignificant in comparison to checking thousands, millions of elements in a linked list if you have large data. Make sense?
Does that have any questions?
And I think this is this is getting a little long. I have planned an hour, but it seems like my planning is a little off. Yeah, I think I'll have to head out as well. I'm going to share the what I wrote right now. And do you want me to implement the push back, or do you want that to be empty so you can try and implement it yourself? That is this one here. And we could also here, and this is one thing, right? You can have public at index and index, right? And the reason I didn't even put this in there is because it's computational expensive. Like if you want to do something like this, just use an array. Like I wouldn't use a linked list for this, so it's not practical. But for practicing, it's a good practice.
Could always for the methods that are not written yet, could always put like pseudocode, like so that way it's like somewhere in between.
I tend to do this. And this is an interesting thing, right? This has to return something, but I don't know what to return. And so you can return null. That's fairly simple. And you can safely return null here because E will, because of type erasure, will be replaced by object, right? An object can be null. So yeah, you can just do that.
And then one last question before I guess we head out. So for space complexity, it just depends on the method, right? Because if you add more variables, then you're going to have, it's going to consume more space. It's going to consume more space, memory, basically. But if it doesn't need to, it's going to be constant because you already are using the things that you have available. Is that the general way?
I don't think I got it. Can you ask it again?
I'm sorry. So I am not as, I'm like still learning about how to calculate space complexity. I'm getting better at calculating time complexity, but
space complexity
is space complexity. My general understanding is that if you don't add any extra variables or things to help you keep track of your data, then it's going to be constant.
Yeah, it's constant. You're not adding more space.
Okay, so it just depends on the method then, the space complexity of each method, whether you add something or not.
Yes. In general, let's say you have n elements, and for each of those elements you add one more. Let's say you add an extra array, right? So per each element, you will be adding one more bucket to that array that you are using to do something else, whatever you're doing. So that means that it grows as n gets larger. The space that you're using, the extra space you're using, also grows larger. So the time complexity will be n. If instead of that you're creating n squared, which that would be awful. But yeah, space-wise, you're creating n times n more buckets. Yes, that's will be n squared. And yeah.
Okay. So basically, the things that we currently have, because we already have enough variables and things, enough pointers, most of the methods that are in this circular linked list should be constant time then.
Yeah, because I am not creating anything else in here to keep. Yeah, most of them will be constant time. We'll have to go one by one. And I don't think at 142, I don't think they really go over space complexity very much.
Yeah. No, I was just curious.
Yeah, okay. I gotta get going.
Oh yes, thank you everybody for being here. I hope you guys learned something or reviewed something. And yeah, this code will be posted on the GitHub. And thank you, Hardy, so much for your time. And it's always good to see how, you write and draw things out, because that helps me and other people, be able to visualize it themselves. So thank you.
Yeah, no problem. Yeah, bye-bye. See you later, I guess.
See you, everybody.